This presentation started as a review of reflected light sensors because I found myself going through it with some new MicroMouses, and it appeared that not everybody knew everything about it, which you sort of assume once you've been at it forever that everybody knows what you're talking about, but that didn't appear to be the case. And when I started to actually think about it to make a proper presentation of it, I found that some of the things that I sort of took for granted were less than ideal. So it's possible that even some of you experienced people will find that your existing methods could do with looking at once again. There's a lot to cover, so please excuse the length, and please ask questions when they occur to you, because otherwise I'll have forgotten what I was talking about, and you'll probably have forgotten what you were talking about as well. So here we go. Right. This is all the things that a MicroMouse sensor ought to have. Fortunately, it doesn't have to achieve world peace as well. Some of these are obvious. Some numbers. The mouse would typically be about half the wall spacing in width and length, so about 45 millimeters is wide and long, and you've got to fit everything in that space. The mouse is likely to weigh around about 100 grams, and you might need 6 sensors. So if they all weighed 10 grams, that's your weight budget gone already. The inertia depends on the distance, on the square of the distance from the center of the mouse to the sensor point, the sensor. So you want to pack everything in tight, as close to the center of the mouse as possible. It's got to be fast. A competitive mouse can be moving at several meters per second, and it needs to be able to detect 12 millimeter or 6 millimeter wide posts at full speed. So it needs to sense the walls every 5 milliseconds or less. Some builders of high-performance mice, and I'm looking at you, Pete, are looking to sense the wall at a rate of more than 1,000 times a second. Is that about right? Yep. Sufficient range. It's desirable to be able to detect walls over a range of at least 2 cells. So you can detect the dead end in lots of time, and you can detect the walls in the cell that you're approaching before you enter it, so you've got time for your solver to run before you reach the decision point. So I aim for a potential range of at least 2 cells. You can get away with less, but 2 cells would be a nice number to be able to do. It's got to be reliable. If you put in a wall that isn't there, it can be catastrophic. It's got to be linear, or at least monotonic. Now, the point of this is that the way the range changes, the numbers change as you get closer and further away from the wall, is part of your KP for your PID controller. So if the slope changes, that's going to change your gain constant in your PID controller. If it's not monotonic, that gets even worse because it changes direction. So your PID controller is going to be really messed up. So you'd have to do all kinds of interesting things to get over that. It's got to be consistent. The position data must be the same every time you're in the same place. Because if it's different, life's going to get really challenging. So it's got to be consistent with temperature, battery voltage, the direction the mouse is pointing, everything else. It's got to have sufficient resolution. If you can only tell your distance the nearest centimetre, you'll find it very difficult. So you want to get down to millimetre precision, or better if you can. It's got to be cost effective. A lot of us haven't got an awful lot of money. If you needed 6 sensors and they cost £100 each, you probably wouldn't use them. And it's got to be easily set up. If each sensor takes a month of dedicated effort to develop and tune for a particular mouse, you're not going to do that for 6 sensors, are you? Hang on, now I've got to do this by hand. Right. There are different types of reflective wall sensor. At least 5. Some are obvious, some less so. Cameras. These are fairly obvious. After all, that's the way we do it. They tend to be heavy and expensive. You may need more than one unless you use some unusual lenses. They may need to operate at something over 200 frames a second, and this requires a large amount of processor power. Adding processor power is arguably cheap and easy nowadays. Adding the software to use it isn't. It could take you more than 1,000 lines of code to sort it all out, and it has to meet real-time deadlines as well. And processor power implies electrical power. That's got implications for your battery life. And electrical power also implies heat. In a half-size mouse, the thermal load may be a limiting factor. I've had custom plastic parts in a half-size mouse soften due to them getting too hot. So I had to give up that particular technique. Time of flight sensors. This is another kind of reflected light sensor. You send out a pulse of light and measure how long it takes to do the round trip to the wall and back. Light travels about 300 millimeters per nanosecond, so you need to be able to resolve time down to the 10 picosecond level. Don't expect to do this at home unless you're a talented optoelectronics engineer with a lot of expensive kit and a lot of time and money. You can buy them ready-made at affordable prices as well. You simply mount them to point in the right direction, send the proper bytes over a serial link, and get a target distance in millimeters back. They don't really care about the reflectivity of the wall, so they're ever so easy to use. But the big issue of them is that they take at least 10 milliseconds to take a reading. It's also not very obvious which bit of the wall you're looking at. I spent a lot of time and effort trying to make them work in a reasonably fast mouse and gave up in the end. If you want to have a very slow mouse, they're a very attractive proposition. But I won't be talking any more about them, just to say the device I used was an STM VL6180X. Triangulation sensors, these are clever. They shine a spot of light at an angle to the wall and detect the position of the spot in the field of view. They're relatively insensitive to the reflectivity of the wall, and they can be made immune to ambient light. But the geometry is a bit tricky. It requires good optics and precision construction. The light source is straightforward, but it needs a narrow beam. A laser would be ideal, but these are heavy and comparatively large, and safety has got to be thought about as well. The sensor is essentially a one-dimensional camera. The best known supplier is Hamamatsu Photonics. They can be a bit tricky to get hold of. Some people have done it successfully, so it could be worth further looking at. I've got very little experience in this method, as I was put off by the optics. The optics are tricky. It can also give you a bit of a problem getting a good enough signal to noise ratio, so I won't be talking about that anymore. Top of the wall sensors. Right. Now then, can you see my mouse? This is a half-size mouse I had a go at. This is the one that got too hot. You see I've got 3 arms sticking out, and each of those arms has got what is essentially a line sensor on it. So I'm treating the top of the wall as a white line. It's been used quite successfully in the past. Back in the day, late 80s, they were very successful. The reason that people don't use them, I think, is that these great big lumps of sensor out over the walls have got quite a lot of inertia. And as most people have in mind that their mouse is going to be incredibly fast from the start, they think this is off-putting. Having said that, the moment of inertia is proportional to the square of the offset from the center. So it's reduced to a quarter of the value when you're talking about a half-size mouse instead of a full-size mouse. And I think it'd be worth considering for a half-size mouse, as the components have got a lot lighter since the late 80s. The surface mount components, bit of carbon fiber like I've used on there, and you could make it very light. However, that's all I'm going to say about the top of the wall sensors for now. We get on to the real thing, the thing that nearly everybody uses. They work by measuring the amount of light reflected off the wall. I've got some rubbish here. I could get rid of that, perhaps. Never mind. Sorry. obviously, the further away you get from the light, from the light source, the dimmer it gets. So if you've got a spot of light on the wall and you move away from it, it will appear dimmer. So the further away you are from the wall, the dimmer the light will be. Now, they have a problem with ambient light. So to cancel that, you need to take one measurement with the light source on and another with the light source off. And if you subtract the measurement with the source off from the measurement with the source on, you'll cancel the ambient light. But you have to do that quickly because ambient light is changing in level. Especially if it's a fluorescent light, it'll be going from full brightness to full dimness 100 times a second. So you've got to get your measurements close together to cancel ambient light. So these reflected light sensors can be fast, cheap, light, and mounted close to the center of the mouse because the only thing that's going and touching the wall is the light. Sorry, somebody talking? No, okay. There are some disadvantages. They're affected by the reflectivity of the wall, so you want consistent walls. And the transfer characteristic is intrinsically non-linear. So as long as the whole of the spot of light is on the wall, and the sensor can see all of that spot of light, the transfer characteristic is going to be inverse square law. So if you double the distance, you get a quarter of the light back. Yeah. And because of that, long range can be a bit tricky to achieve. So for this reflected light, we're obviously going to need a light source. And it's got a whole load of things that we're interested in. But any light source we use has got to be capable of being turned on and off rapidly, so we can do the ambient correction and all that kind of thing. The only viable options are LEDs and lasers. The important parameters you can see up there, well, I'll deal with those one at a time, but those are the things that you need to consider. So the first I call the angle of half intensity, which is a spec sheet value. Yeah. So a typical LED is going to have something like a 10 degrees half angle. So the light comes out over a 20-degree cone. And I hope you can see on there, I've shown the light source here and the wall here, and they're 200 millimeters apart. And that's the size of the light spot you get. Now you can see we're losing some light off the top and we're losing some light off the bottom. So we'll be out of the inverse square law area. You're going to get non-linearities due to losing some of the light. It's also going to mess up your range. So it's not a good thing to have. So here we've got a slide. Sorry about the extraneous stuff. If it was full screen, this wouldn't appear. But you can see here, if we can reduce the light source to a 4-degree half angle, plus or minus 2 degrees, but this is about as narrow as you can get, but there are a reasonable number of LEDs available with this sort of angle. And you end up with a 40 millimeter diameter light spot at 200 millimeters range. And that's entirely on the wall, so you're going to get inverse square law out to 200 millimeters range. Now, if you've got a laser, the half angle is essentially 0. So it doesn't really matter how far away you put the wall, you're going to get the same size dot of light. Very convenient. Lasers are really good like that. When you actually look at this with a real LED, when you can see a visible light LED, you find that this ideal spot isn't necessarily round. One of them, the spot of light you get is basically square with a hollow in the middle. So the light is concentrated around the edges of the square. It's probably a picture of the LED that's inside the chip. Excuse me. Right. The next thing is maximum power output. Now, the more power you can get out of the thing, the brighter the light is. So the bigger is better. However, there are considerations of eye safety, especially with a laser. Lasers should be limited to 2 milliwatts maximum, because sooner or later you're going to end up with it pointing over the wall and possibly in somebody's eyes. And blinding them would be a very bad thing. Some of the infrared LEDs need careful consideration, because the power output can be very significant and can cause safety problems. So you need to think about how long you're leaving the LED on for. If you only leave it on for a very short time and then turn it off for quite a long time, the average power is low enough and it shouldn't give you any concerns of eye safety. But if your hardware or software can fail in such a way that the infrared is turned on at full power continuously, then you can end up with potential eye issues. Now, the wavelength, your choices are infrared and stuff you can see. Infrared LEDs have got lots of advantages and lots of people use them. They're cheap and you can buy them down in the 4-degree beam widths. They're a very good match to cheap silicon sensors, and the infrared level from sunlight is less than the light level. So sunlight delivers less infrared than it does light. Good old-fashioned theatre lighting with incandescent lamps delivers considerably more infrared than it does visible light, but that's probably not a problem nowadays. The biggest problem with infrared is you can't see it. So you don't know what's going on particularly, and you can get multiple reflections and things like that that you can't see. You can't tell whether you're losing some of the light off the top of the wall, and you can't even tell if the spot is circular and even unless you've got special technology. A safety consideration is that because you can't see infrared, it doesn't make you blink or turn your eyes away. So it doesn't have that advantage. When you come to visible lights, you've got lots of available colours, but choose red because it's a much better match to the silicon sensors and you can still see it. There is at least one red LED with a beam width of 4 degrees, which I think quite a lot of us are using. Other possibilities, you could use UV. It's got the worst features of all the other LED colours, but also you need to wear safety goggles as well, so don't use that. White LEDs often use a phosphor to convert a blue or UV LED to white. Now those phosphors are slow in turning on and off, so don't use them. At other wavelengths, you don't know what the reflectivity is going to be like, you can't tell. And certainly you can't use radio waves or X-rays or anything like that. So they're not really options. Right, next thing we've got is size and weight. I think you're probably all familiar with size and weight of LEDs. Lasers are bigger and heavier. The ones you can get cheaply, about 7 millimeters diameter and 15 millimeters long, and weigh 4 times as much as the LEDs. Cost. LEDs can cost you between about 10 pence and £1. Better ones cost you more. You can buy laser modules as cheap as £1 on eBay, but you can spend as much as you like for the professional ones. Summing up the choice of light source, I prefer visible LEDs. I like to see where my light's going. Most people seem to get on fine with infrared, but there are some visible laser-based sensors out there, which I think are particularly good, but a bit heavy. Right, so we dealt a bit with light sensors, with light generators. Now we can talk about sensors a bit. Again, we've got the same kind of considerations. But the first thing is they've got to be matched to the light source for spectral response. So don't use a sensor with an infrared filter on it if you've got a visible light. Usually the ones with infrared filters on look black. So they've got something in there that stops visible light. They're not going to work with a visible light sensor. There are things called cadmium sulfide photoconductive cells, which have been used on mice in the past for line following and stuff like that. They are dead slow. Don't use them. And they're also pretty much prohibited from going into landfill. They don't like the cadmium in the landfill anymore. So the only viable options are photodiodes and phototransistors. And here's the parameters that we want to see when we're talking about those. Now, the angle of half sensitivity. This is the equivalent of your half power level parameter for the LEDs. And you can buy really narrow angle ones. You can buy 4-degree ones. I hope everybody can see that. The sensor field of view is in yellow, which is probably not the best choice. What we've got is the field of view of a 4-degree sensor alongside the illumination from a 4-degree LED. They're as close to each other as they can realistically be. There's a 1 millimeter separation between them, and they're 5 millimeter parts. Now you can see at 200 millimeters, the sensor can see most of the spot of light. But at 40 millimeters, it can't see any of it. So if you want to be able to see a wall at 40 millimeters, this isn't going to work. You could try tilting the sensors so that at 40 millimeters, the sensor can see all of the light from the light source. But the trouble with that is it can't see much of it at 200 millimeters. So there is no good compromise. There are things you can do to use the overlap area to modify the inverse square law for you. But for me, that gets really complicated and I really don't want to do it. So I don't use narrow angle sensors. Now, there's plenty of sensors out there with a 60-degree half angle. Now, what this basically means is a flat piece of silicon with no lens over the top. So it's as wide an angle as you can get. And there's plenty of devices out there that are just a silicon chip in plastic. And you can see here that the sensor can see all of the spot of light at all sensible distances. It might lose a tiny bit of it when you're a millimeter or two from the wall, but don't worry about it. Now, the big disadvantage of that is that because, I'm not sure how this is going to work, you can see how wide an angle the sensor can see. So it can see light up here, above the wall. Yeah? So it's more sensitive to ambient light. It's going to pick up more ambient light. But there's things you can do about that. You can put a blind in the way here to blank off the areas you don't want it to see. Yeah. If you want to get really posh, you can use mirrors, blinds, and lenses to get any field of view that you want. But start off with a wide angle one, and you've got a much better chance. Now, the other sensor, it could be a tiny chip of silicon on a really cheap one, or photodiodes. The ones I can afford go up to about 5 millimeters square. You can buy them as big as you like. I mean, as literally the things that go on your house to generate electricity are photodiodes. So as big as you like. The bigger ones are more tolerant of alignment errors. Yeah? A tiny sensor with a lens to collect the light will give you a small field of view. Speed, faster is better. A fast mouse could be moving in several meters per second, and again, it passes a 12 millimeter per post in a few milliseconds. You might want 2 or more readings while this is happening. So that's why you can't use cadmium sulfide cells. When I come back to this later, when I'm talking about electronics, you'll see you want the whole process to be as fast as possible. So we need a fast sensor. Phototransistors have settling times of the order of tens of microseconds. Photodiodes settle in the order of 1 microsecond. So photodiodes are much faster. Sensitivity. Now, I like to think in terms of electrons per photon. And photodiodes are going to give you a little bit less than 1 electron per photon, because you lose the odd one here or there. Phototransistors are exactly equivalent to a photodiode feeding into the base of a transistor. So whatever the photodiode current is, it's multiplied by the gain of the transistor. So you can expect currents that are 100 times bigger. So you get bigger currents, but they take longer to happen. But the worst bit about them is the linearity. Now, the reason we care about linearity is because the ambient light can be so much larger than the desired light signal and can vary over a wide range from looking directly at the light and directly away from it, away from it. And as the mouse moves, that's almost inevitable. So a photodiode is almost intrinsically linear. The slope will be the same in terms of photons per electron, however many photons are passing. Phototransistors are less linear. The gain of the transistor changes with the bias current. You can see this is a typical graph here. Right, so you can see at low currents the gain is down, and at high currents the gain is down, and there's an optimum current at which the gain is maximized. So with a photodiode, a certain change in light level might give you a 1 microamp change in output current in the dark, the same change in output current in a lighted room, and the same again in full sunlight. So if the light changes by a certain amount, it's going to give you a certain number of microamps of change. Now, if you look at this curve, if you've got a change in current here, you might get a 70 microamp change for a particular light change here. You might get a 100 microamp change for the same change in light, 100 microamp change for the same change in light here, and less again here. So you could get 30 or 40% change difference in the change in light level, depending on the ambient light. It's a sort of intermodulation effect for those who are radio people. Yeah. This is why I don't use phototransistors for reflected light sensors. They're fine for a line sensor where you can put a blind over the top, a shade, to keep the ambient light out. But for a reflected wall sensor, there's nothing you can do about it. So linearity is important, and that's why I use photodiodes. Okay, wavelength, etc. So silicon is most sensitive in the infrared, but a lot of them will give you good responses with red light. This is why we use red light rather than blue light or green light. We use red light because it's a better match to the silicon. Quite a lot of them you can buy with infrared filtering, which is good if you use infrared, but don't do it if you're using visible light. Okay. So you can buy photodiodes and phototransistors as small as 0603, little tiny things. And you can buy photodiodes as big as 40 millimeters diameter, I've got down here, but bigger if you want. The bigger the area of silicon, the slower it will be. But don't let that worry you, because a photodiode's fast enough anyway. The little 5mm cylindrical photosensors tend to have a narrow field of view, so be careful with those. The wide field of view, the flat ones, come in mostly in surface mount packages in various sizes, and the weight is basically proportional to the size, and the 5mm cylindrical ones are about 0.5 gram, same as the LEDs. They can be as cheap as 10p for the smallest, and the ones I use around about anything up to £1 each. So we've talked about the light source and the sensor. Now it's time to talk about how we actually drive them. I'm treating LEDs and lasers as the same here, because provided you've got the right kind of laser module, it doesn't make any difference. They need to drive it with a high peak current to generate the maximum possible light just at the moment when the sensor wants to look at it. Because at any other time, it doesn't matter what the light is. We only want bright light at that moment. Now, most LEDs can tolerate a peak current of about 1 amp for a very short period. So we're talking about a peak current of about 1 amp. That current has got to be isolated from the main supply so you don't get unnecessary supply ripple. So if you take 1 amp instantaneously from one of those batteries, the supply, that battery supply will dip very considerably, because they're basically current limited to about 1 amp anyway. So we've got to have a local storage so we don't make the battery voltage dip and possibly reset the processor, which would be a real pain. We've got to keep the light on long enough for the A to D converter to do its conversion. The current pulses have got to be the same, because if you're getting different size current pulses for different sensing instance, you're going to put noise into the signal that you're reading off the wall. So it's important that we put uniform pulses out, high current, without affecting the battery, and it's on for long enough for the sensor to read them. Now you can make the duty cycle low, so the average power in the LED is within its capabilities. So if the LED can cope with, say, 250 milliwatts continuous power at a full voltage of 2 volts, the maximum average current is 125 milliamps. So if you want a 1 amp drive current for part of the time, you've got a maximum duty cycle of 1 in 7. So you've got to leave it off for 6 times as long as it's on. If you want to sample every 0.5 millisecond, the maximum on time for the LED is 42 microseconds or so. So if you put an amp through it for 42 microseconds, you can't do it again for another 0.5 millisecond. So you've got 42 microseconds to take your measurement, and some external ADCs with slow drive software will take longer than this. I think Paul managed 300 microseconds or something with his Python mouse. So that's an issue. Okay, this is how it's done classically. I believe this is how it's done on UKMARS bot, and it's been done like this on every mouse of mine up until the current one, because I started looking at this in detail and decided this is awful and I needed to make a change. So let's talk about what it does. This switch can be a transistor or an FET. When you close it, the LED is on. When you open it, the LED is off. Vreg is a regulated voltage within the mouse. If it's not regulated, the light output is going to change with this voltage. And it's got to be comfortably more than the forward voltage of the LED. The forward voltage of the LED is more for visible LEDs than infrared ones, But even for an infrared LED, it can be about 2.5 volts at 1 amp. It's going to vary, so between LEDs it could be at least 10% different in forward voltage. It's a bit temperature dependent as well. Our limb, this one here, should be selected to limit the average current from the supply to a safe value. Safe could mean doesn't blow the LED up, or could mean doesn't permanently damage your eye. For a 5 volt supply, I typically use 47 ohms there, which limits the current in all cases to about 100 milliamps. And if the LED is working, it's typically 50 milliamps. So I'm driving the LED average at about 50 milliamps. I can't do more than that on average. Most LEDs will cope with that indefinitely. And the reason you put in a physical limitation there is because sooner or later your software is going to turn this switch on and leave it on. That could be because something has crashed at an unfortunate time, or there's a brownout happened, or you haven't written perfect software, or an interrupt routine has caused a stack overflow, or anything. Leave the switch on, and if you haven't got a limiting resistor here, you'll blow the LED out. And it's really embarrassing when a software error blows your hardware up. Okay, C, this bit here is our energy storage. That's charged through there with a time constant of R lim C. Now we want the capacitor charged up to a stable voltage before we turn the switch on. Because if it hasn't charged up to a stable voltage, you're going to get a different current through the LED. Okay, you can get away with shorter times, but if you do that, you're going to have to make sure the time interval between switching the LED on and the time for which the LED is on is exactly the same every time. And I mean properly the same within a microsecond or so. That's hard. 10 microfarad capacitance with 47 ohm resistance gives you a time constant of 470 microseconds. So you may get away with a 10 microfarad capacitor and time between pulses of 2 milliseconds or more. 5 milliseconds would be better. You can reduce R lim to get a shorter charging time at the risk of your LED or eye. You could also decrease the value of C at the cost of the energy available for the light pulse. When the switch closes, C discharges through RDIS and the LED. The peak current should be as high as the LED can tolerate, and probably about an amp. The peak current is VREG minus the VF for the LED divided by the discharge resistance. Now, discharge resistance is carrying an amp or so of peak current. I don't trust 603 resistors at that level. I always use a 1206 there. With a 5 volt supply, the discharge resistance should be about 2.2 ohms for a visible LED, red LED, and perhaps 2.7 ohms for an infrared LED. But that discharge resistance is added to by the ESR of the capacitor. So that's the equivalent series resistance of the capacitor. And if you've got an electrolytic capacitor, as in fact I've shown here, the ESR could be more than that. So that will limit your discharge current. I use a ceramic type, and unfortunately ceramics come in all kinds of shapes and sizes now. Real pain. Bigger is better, but I get away with an 0805 there. As this discharges, the voltage across it drops, and so does the LED current. LEDs are fast, so the light will get maximum intensity within about a microsecond and will then fall off as the discharge current falls off as the capacitor discharges. The fall in the LED current isn't exponential, but the bigger the value of C, the slower the fall. There's a high peak current around here, an amp or so. Right? So use heavy gauge wire and make sure that none of this wire, especially this bit, appears in other sensitive circuits, because you will get voltage drops between here and here. And if your ADC signal is completed through that bit of wire, you can cause problems. Okay, now this is the voltage across C with the system that I was running here. The voltage across the 10 microfarad capacitor has dropped by nearly a volt during the 8 microseconds that the LED pulse is on. And then it slowly recovers. I say slowly, that's what the recovery looks like. These on times are 5 milliseconds apart. And the recovery time constant is C times R ln. If you try reduce the discharge slope, this one, by increasing C, you'll slow down this bit. And if that hasn't recovered by the time this pulse comes in, this is 5 milliseconds. Some people want to do it 1 millisecond. If that hasn't recovered by the time the next pulse comes in, you're going to get a different level of LED current. So that's where your timing becomes critical. I don't recommend it. So we could talk about the switches. Now, this is the classic switch. I think this is what's in a UKMARS bot. I'm probably going to upset people by what I'm going to say next. Never mind. Any transistor you use here has got to be very carefully chosen. Don't just pick up what's at hand or cheap. Something like a BC547 or a BC337 will not do. The peak current is 1 amp or more. The collector-emitter saturation voltage of a BC547 is 0.6 volts at 100 milliamps and more at higher currents. This is taken away from the voltage available for the LED. So 2.7 volts of LED forward voltage plus 0.6 volts of loss in a switch means that you can't get 1 amp through the LED off a 3.3 volt supply. Can't do it. Okay. There are better transistors, but they cost more, and they still might not be okay. For example, the ZTX653 has a saturation voltage of only 0.3 volts at 1 amp. Saturation voltage is the voltage between collector and emitter when it's fully on. The ZTX653 needs 100 milliamps of base current to do this. And the available current from most microcontrollers is less than 20 milliamps. So you can't drive it fully on. You'd need an extra transistor to provide that base current. And that adds cost and complexity. The value of R1, just to finish off, is chosen to limit the current from the I/O pin. So we don't want to damage the processor. If the controller can supply 20 milliamps without damage and is running from 5 volts, the resistor should be about 55 divided by 20 milliamps, about 250 ohms, say 270 or 220. This is optional with most modern microcontrollers because they can pull the I/O pin all the way down to ground. But if you use it, 10K is a good value. It doesn't actually make the circuit work any better, but it doesn't cost you much. But I personally wouldn't use a transistor. I think you're buying yourself a lot of grief. Unfortunately, the options, if you must have through-hole devices, are very limited. An MFET, they're a good solution. You can get something with an on resistance of 0.1 ohms. So it's 0.1 ohms between source and drain. So you're only going to lose 100 millivolts of the available voltage. You'll need a gate threshold voltage of 2.5 volts or less, so you can drive it directly from the microcontroller. There are lots of types that will do the job, but they're nearly all surface mount. If you've got a through-hole, you're probably looking at a TO220 package costing more than £1 with weight and space costs. I use SOT23 types at about 50p or less. Function of this resistor is to pull down the gate and ensure the transistor is off during controller reset. If you don't do this, the gate of the FET will float and the FET may turn on. An extra few hundred milliamps, depending on how many LEDs your system's got during a processor reset, could cause issues. It might prevent your processor from getting out of reset, and resistors are cheap. So afterwards, if anybody's interested, I can talk a lot more about transistors and how they sort of work sometimes, but you're unlikely to get repeatable results. The bit you all want to see is here. This is the light output waveform. This is the actual light waveform that you get from the LED from this conventional driver. And you see the LED, the light output is dropping fairly rapidly there. Yeah. If you want to sense a peak light output, you've got to do it in a couple of microseconds. It's already down here at 10 microseconds. And if you've got some kind of unfortunate system running, sad to say it, Python or something like that, it might take you a few hundred microseconds to actually read the ADC, by which time there's no light. So people have been bitten by that in the past. Some ADC systems, the driver software hasn't been designed very well, and they do a complete reinitialization of the ADC before each sample. So they can take a long time. Right. So I read a lot about this. There's a lot of problems here. If you've got jitter in the time when your ADC actually reads this signal, that's going to come up as a noise voltage. You've got to read it at a very consistent time after you've turned the LED on. Short time is better, but even here, you don't want it jiggling about up and down this curve. You want it at a consistent time. That may be easy, but if you've got interrupts going on, it can mess you around. I unfortunately have DMA transfers going on, which can cost me 100 nanoseconds randomly when the odometry signals come in. If I was doing the odometry with interrupts, I would be worried about it. I'd probably want to turn the interrupts off before I do one of these things.
Mm-hmm. Duncan?
Yeah?
Is that drop a function of the sensor, or is it the capacitor supplying the LED?
This is the capacitor supplying the LED.
Right.
That's the actual light. This is measured with a photodiode. The photodiode is fast enough to see what's going on. And nothing's moving, so it's the same signal all the way through. And photodiodes are pretty linear, as I've said. Yeah.
Okay. Thanks.
So I witnessed a lot about this and thought, well, let's have a better circuit. And this is my better circuit. So the existing things clearly work. Lots of people have made mice that work with them. Lots of people have sworn at their mice that work with them. They've got a few disadvantages. They need a regulated voltage supply, and 3.3 volts is marginal at best. 5 volts is better. The LED current is not particularly well defined, and that means that the LED light isn't particularly well defined. You get a lot of variation between individual LEDs, and if you're using the transistor driver, between individual transistors. So this is my solution. So rather than start with the lowest regulated voltage and try and get a constant current, because current is what we're interested in, I start with a constant current. And the way it works is this. We've got an FET here, doing all the normal FET things. When the gate is sufficiently more positive than the source, it'll turn on. And the amount it turns on will depend on that difference in voltages there. So when the I/O pin goes high, the gate will follow it, and this will turn on. Current through the LED will also, that's going through this FET, will also go through our sense. And at a certain current, the voltage across our sense will be enough to turn this transistor on. Around about 0.6 of a volt, it'll turn this transistor on. When this transistor turns on, it pulls down the voltage here and tends to turn this FET slightly further off. So it will settle at whatever current is required to turn this transistor on. The excess voltage is dropped across this resistor. Okay? So if you make that about 0.56 of an ohm, this transistor will turn on at about an ohm. Yeah? You need this resistor to be about 1 kilo ohm. You make it bigger than that and everything will get a bit slow. Make it much smaller than that, and you're talking about loading on the I/O pin and stuff like that. We've got a pull down resistor here, just the same as we had with the NFET circuit. And the important thing about this is it doesn't care what the supply voltage is. The current is defined by this resistor here. We do exactly the same in terms of storing energy in a capacitor and discharging it through this. But we can tolerate, if we've got a 9-volt battery supply, which is typical for people nowadays with these little PP3s, we could tolerate that capacitor voltage dropping down to maybe 4 volts before this current will change. Yeah? So we don't really care what that voltage is in that range, as long as it's 4 volts or more. Doesn't matter whether the capacitor's had time to charge up or anything like that. This is just going to deliver 1 amp while this is on. You don't need a limiting resistor, you don't need an R-lim, so this has got all that in it, so the R-lim can just be a bit of PCB track. And the great thing about it is this is what the light output waveform looks like. So I can sample this anywhere in here. Yeah, my jitter on the ADC timing is irrelevant. My jitter on the time between samples is also irrelevant because I don't really care whether the capacitor has charged up to its full voltage or not. It's cost you an extra transistor. BC849 is going to cost you about 5 pence. Doesn't weigh anything to speak of. Yeah, it's going to be a bit difficult to do in through-hole components because getting a through-hole FET with the right kind of capabilities is the challenge. But if you surface mount, this is the way to go. Means you don't have to have an extra voltage regulator if you're trying to run your processor off 3.3 volts. You've all gone silent. Okay, I'll assume you've got...
We're enthralled. We're enthralled, Duncan.
In that case, I shall go on to the next bit, which is the photosensor. Here we go. Now, this is what I have been using for years, and I think quite a lot of people have been using it as well. When I looked at it, it's actually horrible. Excuse me. Right. Excuse me, sorry. So let's explain what it does. The photocurrent through this photodiode passes through the load resistor and produces a voltage across it, which is what the ADC looks at. The current through here is a tiny leakage current plus the photocurrent. This is assuming photodiodes. And we're feeding it off the microcontroller supply. So we've got a regulated voltage here. So because the current through here is basically proportional to the light on it, it's a constant current source. So in terms of noise on the microcontroller supply, that noise is divided by the ratio of this resistor to that high resistance constant current source. So you get quite good supply rejection from this. In theory, the maximum voltage you could apply to the ADC is the microcontroller supply voltage. This is why people do it like this. They don't want to overload the ADC input pin. Unfortunately, if you put enough light on the photodiode, it's a photovoltaic device and it will generate a voltage across it and it will actually raise this above the microcontroller supply. But in practical terms, that's never going to happen. And even if it did, the current available isn't enough to do nasty things to the ADC input. Make sure you get this the right way round. If you put it the wrong way round, you'll get really sort of weird results. If you use a photo transistor instead of that, make sure the collector goes to the supply. And that's where you'll notice the thing that started to ring alarm bells for me. The smallest voltage you can get across the photo transistor is its saturation voltage. So the closest that this can get to there is about 0.4 of a volt. It can't get up to full ADC range if the ADC reference is a microcontroller supply. Now then, just talk about this resistor a bit. You use this to tune the sensitivity. So if you're getting too big a signal, you make this smaller. If you want a bigger signal, you make it bigger. But you can't make it too big. You limit it to about 10 kilo ohms because the ADC can't be fed from an impedance that's higher than that. So 10 kilo ohms is your maximum, and you tune the sensitivity of your sensor down by reducing the value of this. Right? Now, what is absolutely horrible about this is that at high light levels, the bias across this device is essentially 0 volts. The devices are specified with a particular bias across them, typically 5 volts across them. And when you get down to less than about a volt, they go horribly non-linear, and the photodiode capacitance increases dramatically. So you want at least a volt across your sensor device. Yeah? And if you're feeding it from the microcontroller supply, you haven't got that. So it's actually very difficult to get this to register the full ADC range. You're limiting your dynamic range. A better solution. Doesn't look very complicated, does it? Basically, what we're doing is we're feeding the sensor off the battery voltage. So instead of only having 3.3 volts here, you've got some headroom. You might have 9 volts here. We still need decoupling, but you can share the decoupling with some other sensors. You probably can't do all of them, but you can probably do 2 or 3 sensors off one pair of decoupling components. The fun thing about it is the battery voltage is going to go up and down, and some of that is going to get through to here and may possibly cause you some changes in your signal here. You decouple it to get rid of the fast signals, and your ambient correction will get rid of any slow signals that get through. And as I say, the photodiode is pretty much a constant current device. It's not affected by the voltage across it. Anyway. So this is my proposal as a better photo sensor. Doesn't cost you much. If you wanted to run all the sensors off one component here, you'd be better off putting something like maybe a 7-volt regulator in there. But you want at least a volt across your sensor for all conditions. Yeah? And amazingly, that's all I've got to say. Questions, please. Part 2 will be different.
Just before I forget, what on that photodiode circuit, what would be a typical value you would use for R1, the load resistor for the photodiode?
I typically be using 10 kilo ohms there because I want maximum sensitivity. And R2 would be about 1/5 of that.
Thank you.
C1 is 10 microfarads or more, whatever you've got space for.
Well, thank you. That's a very comprehensive introduction. Go on.
Yeah, quick question. With your better photo sensor, I still can't see how that is stopping the ADC input going above the dynamic range that it's supposed to have. So if your battery voltage is 9 volts coming down through R2 and then through the photodiode, what's to stop that ADC input floating up to 7 or 8 volts, which would be far too high for the microcontroller?
There's 2 things are going to happen there. First of all, you select R1 so that your worst case ambient light and your shiniest wall as close as possible to your LED gives you 3.3 volts across here. Yeah? So the voltage here is determined by the current through R1, and you adjust R1 so that condition, the biggest possible light your sensor is going to see, gives you 3.3 volts here. Yeah?
Yeah, I'm not sure about that.
Well, at a certain number of lux, you're going to get a certain number of microamps through your photodiode. Yeah?
Right. Is this the same if we're using a phototransistor, or is this specific to photodiode?
If you're using a phototransistor, it's going to be less well specified. But if you've got the time to tune R1, then that's fine. So, as I say, you adjust R1 to give you that number. Because what you actually do, I mean, this is part of part 2 now, right? But what you actually do, you've got a dynamic range on the A to D converter of, I don't know, 12 bits or something, yeah?
Yeah.
And you want to make sure that you only just hit that 12-bit resolution in the worst case light. Because if you go over that, you're going to get non-linearities, and your ambient cancellation isn't going to work. Yeah?
Okay.
So that same constraint stops this voltage from going above the required level for the microcontroller.
The thing about the photodiode circuit is that it's not, with a phototransistor, you can think of the phototransistor as permitting current to flow from collector to emitter, or vice versa, if you wish, depending on the amount of light. The photodiode isn't doing that. The photodiode is generating current.
Now, completely disagree with you there.
Go on.
Right? It's electrons per photon, yeah?
Okay, fine.
As long as it's reverse bias, it's not generating anything. It's just letting the electrons through.
Okay. But it can't go up to VBAT unless things get completely out of hand. Is what I'm trying to say, right? So if you connected a phototransistor in place of where you've got PD1, then you could certainly have it climb up to VBAT quite relatively straightforwardly, but that would not be the case with a photodiode, right?
I don't think I quite understood that.
Tend to think of a phototransistor in this circuit as being more like a variable resistor than this, which is a voltage generator. And so...
No, I'm sorry, Pete. The photodiode isn't a voltage generator because it's reverse biased.
You can't have it both ways, Duncan. Either it's generating volts, electrons, volts, depending on the amount of ambient light, or it's creating current. You seem to contradict yourself.
It's reverse biased, Peter. It's not generating anything. So you've got this lump of silicon, and until you shine light on it, it is a high resistance. It's leakage current only. When a photon arrives, it generates a whole electron pair, so there is a current flow, right? But we're not putting it in a mode where it's generating a voltage. That would be a forward bias situation or an open circuit situation.
Okay.
So the point of it is, the current here is determined by the light, and that's true for both the phototransistor and the photodiode. If you give them 1,000 lux, they'll give you however many microamps, milliamps, whatever it is, yeah? As long as they're reverse biased.
Mm-hmm. So is what you're saying that what's happening is the more photons that hit the diode, the more leaky the diode becomes and effectively leaks backwards.
That's a good way of thinking it, yes.
Yep. Okay.
It's always reverse biased. It never gets a chance to generate a voltage, right? But it just allows more electrons through. So that's part of it. You choose R1 so this voltage just about reaches the 3.3 volts. But also, every microcontroller you can buy is going to tolerate a certain amount of current into its inputs. Typically, it'll tolerate 10 milliamps into their inputs before they blow up. So if you've got a photodiode here that's only going to generate, I don't know, a milliamp in direct sunlight, it's just not a worry. I say generate, pass a milliamp. Yeah. I've scared everybody off now.
I think one of the things that might be useful is, I don't know whether you've got typical curves for photodiodes, not necessarily tonight, Duncan, but I think I always found phototransistors easier to reason with, and I'm not entirely sure why that is. I did the theory at uni, but photodiodes are a bit magical, sort of. I understand exactly what you said about the photons generating electron hole pairs, and therefore there's obviously generally a relationship, maybe a proportional relationship between light levels and current flow. And that's, I guess, what you're using to limit the voltage on the ADC input is the fact you never, you control the input light. That's what you control with. You control the current and therefore control the voltage across R1.
Absolutely right, yes. I mean, there is a worst case input light, which is direct sunlight on the thing. Yeah.
Yeah.
And that's the level of ambient that you probably ought to design for anyway, because sooner or later you're going to go to a venue where you're going to get direct sunlight on the mouse. I think Worcester had some of that problem this year.
Yeah, it was tricky. It was tricky to know whether, because we closed all the blinds, I think, at one point at Worcester.
Yeah.
So it's tricky to know exactly what effect it was having on the mice.
And by the time you get to direct sunlight, you're in a whole world of hurt anyway. You've got about 100,000 lux. Whereas in the Japan contests where they often have camera lighting for cameras, I think they say that people should be expected to cope with the order of 1,000 lux or something like that. But so direct sunlight is going to kill it, right?
Well, we have had success in direct sunlight in the past with some of these systems.
Okay.
The other thing to just ease people's minds a bit is don't forget R2 is going to limit the current anyway. So if this is 10 kiloohms and this is 2 kiloohms and it's a 9-volt battery, you can't put more than 4.5 milliamps through this resistor anyway, whatever you do. And modern microcontrollers, they'll cope with that level of current going into their inputs with no problem. They've got static protection systems inside them to tolerate that.
Okay. So it's always good to see different circuits for these things. Well, I for one will be looking at that and see if it. Yeah, I don't understand it. That's the problem, and I'm not an analog person, and if it works like that and I put it together and it works, that's fine. But I wouldn't be able to design it. I wouldn't be able to say, oh, R2 is obviously too small. I try to. So we have been experimenting with at least the other part of this, which you brought up, which was constant current fed sensors, and all the sensors on Mr. Fusion are all run off the battery and run off a constant current source, which is they do a diode specifically for that, so you can get them rated at different currents, and it's just a surface mount diode that breaks down at a specific current. So we run it off of that, and that seems to run quite well because it's just a single. It's literally just so it looks a bit like your constant current circuit with the diode replacing the transistor that you've got in there doing that. And the resistors. So that's an interesting one. But yeah, I do like that because you can run it straight off the battery. That takes a lot of the noise because you're high current switching. You're generally trying to run that off of your regulated supply, which goes straight back to the processor. So I think that bit of it is definitely worth worth doing. But it's difficult. Every single one of our mice has different sensors on it because we just change them to see what is. And we find them all. We've not found one that hasn't worked or hasn't reasonably worked. They worked okay at the various competitions, and so that's interesting. But I've never used. We've used a photodiode with a built-in amplifier in the same package, but that outputs a voltage directly, so you literally get a voltage out. But I've never used a photodiode in one of these.
Duncan, do you have a suggested part number of something that you use for the photodiode?
Hang on a minute, I'll see what I can find you. Just a sec. It might take me. Talk amongst yourselves.
Yeah, I think I don't know how everybody else deals with. I quite like Duncan's graphs of the spots on walls and stuff. I think some of you would have seen the photos where I used a Raspberry Pi with a no IR camera to take photographs of the spots on the walls.
Mm-hmm.
I think lining up, I mean, that's tricky, especially for, I mean, it's a relatively cheap solution to get a non-infrared camera, but then you're sort of trying to line up the sensors. And that whole sort of exercise, I'm not sure whether anybody's got a set of instructions about how you do that, apart from trial and error.
I'm sure Peter's put out a thing about that in the past.
Way back in the mire of history, which is the MicroMouse online website, there's almost certainly enough stuff about it. But the thing about that is that it's all been, as I have found stuff out, I wrote it up, and so it's not very coherently presented. The business of overlapping the spots is important, so it's a good idea to mount your emitter and your detector coaxially as close together as you can get them, so that the overlap of the spots is least affected by distance. You may wish to point them one way or another ever so slightly so that they work best at some optimum distance, and then live with the fact that they will no longer respond quite the same when you're close in or far out. If the whole sensor geometry thing really is a bit of a rabbit hole when you get to it. And the most important thing really is to build some test samples and try them on a bit of breadboard. If I'd thought about it, I would have had my box of bits to hand, but somewhere I have a box with dozens of pairs of emitters and detectors, which I've put into holders so I can plug them into a breadboard and compare one emitter with another detector and all kinds of different permutations. And it's no good just poking them in and kind of angling them about right. You need this thing. I was going to say, you need this thing to be consistent if you want the best results. Not everybody's quite as worried about it as I am, perhaps, but that's what I do, right? A lot of rigorous testing of these things. And the thing to do, I mean, Duncan makes lots of great points about the sensors and their arrangement and their behaviors. You will need to consider them in the context of your own robot. So on my Decimus robots, where I know that I can sample in 5 microseconds or 10 microseconds at the most, I have never had cause to worry about the inevitable droop from the reservoir capacitor, for example. So I don't worry about it. If you're on a system that can't sample that fast or can't sample that soon after the emitters have gone on, then these things are a problem. I would say, though, that over time, these transient behaviors settle out reasonably quickly. You won't get the same response. You won't get as good a response. You won't get the same dynamic range as you would if you had done it all, at that instance and done it all better. But the droop on the reservoir capacitor will come to a steady state, and you will get a consistent reading over time. And it only takes a few seconds to reach that steady state. At the risk of appearing defensive, for those of you who've got UKMARS bots and now think that you've got crap sensors on them, it's only partly true, right? All design is compromise. And as Duncan said, finding appropriate FETs for through-hole mounting in boards like that is not an easy thing, and they're not as cheap as the transistors. So there's a transistor on there. Is it ideal? No. Is it easier? Yeah. Oh, yeah, definitely. Right, and much more accessible. I would not use that circuit in a high-performance contest robot. But that's not what UKMARS bot is. And that's why UKMARS bot has a completely separate sensor board. If you want to make your own constant current surface mount, whatever sensor board, make one, bung it on there, and away you go.
The standard transistors, the BC377s, the sort of accidental things happen. The amount of collector current is the gain times the base current. Yeah. And if the gain available is, I don't know, 50 or something, and you've set it up with a milliampere base drive, you'll get that certain collector current, but it will actually be a constant collector current, right? So you accidentally have made a constant current drive because the transistor isn't being turned fully on. Yeah. The cost of that is that you're not getting as bright a light, but at least it's not changing with time. And the other cost of it is that different transistors will give you different amounts of light. I'm being an electronics engineer, I'm trying to design something where everyone turns out the same. But in a hobbyist environment like we often are, that's maybe not quite so important.
So it is a pain. I specify the 337-40. They're in the different gain buckets, and if you have a different gain bucket, it'll be different. Even so, there's a 2-to-1 variation in DC current gain for those transistors. But it is what it is. It works. And can it be improved? Absolutely. And please do. Right? Improve it, make a board, and add it to the repository on the UKMARS bot site. More than happy to see that.
You were going to mention a photodiode part, was it? You asked Peter.
I think I just put it up on the chat.
Oh, right, okay.
It's a QSB34CGR. Its RS number is 8050508, and RS wants 69p for each one.
Okay.
I should say, if you go trolling around Japanese MicroMouse websites, as I am wont to do, there are two, and you look for stuff about sensors, there are two interesting things that you see. One is the most common emitter that they emitter is, I can't remember the part number, it's one of these like the QSB thing, it's an OSI something emitter, which everybody uses for preference because it's got just the right wavelength, it's got a beautifully shaped spot, it's got a nice narrow beam, and it's only available from one shop in Tokyo. So you can forget that, right? And the other thing that they use, or what quite a lot of people historically have used, is a phototransistor, the TPS601A. And they use it because it's actually one of the most linear of the available 5mm phototransistors. That was stopped being made, I don't know, maybe 10 or 15 years ago. And so I can only assume that somebody has a big box of them somewhere in Japan, or they're buying knockoffs from China, in which case there's no telling what's actually in the can.
Right. Okay.
I've just remembered something else. If you want through holes, there's something called an SFH205, which is a similar sort of beast, but in a sideways looking through hole package for your photodiode.
Okay. A quick comment on the required speed that we run at. Obviously, the speed is really only required to set the distance you are forward to find where the edge of the thing is, but you only actually need that edge at the end when you're just about to turn into a corner. So you don't need to be able to find a post when you're hurtling along at 10 meters a second or whatever it is that Pete can do in the middle of the maze. You won't be looking for that post in the center of the long straight. The only time you're looking for that post is at just before you turn at the other end, where you're going much slower. So it's that speed that you really need to pin down exactly where you are so that you turn at exactly the right time.
I hadn't quite clocked that, Derek, but yes, you're entirely right there.
Yeah, so that just reduces the speed that you can work with a bit.
That may not be quite as true for wall followers.
Mm. Oh yeah, no, that's a different thing. But they wouldn't be doing that sort of speed because they have to be able to turn as soon as they see the corner. So they're restricted in their speed, aren't they? Unless you're using some memory type thing. You can't go faster than you can turn around the corner. Otherwise, you'll see the corner and not be able to go.
Bernard gets around at a fair old leg. I mean, even at top speed, D5 only turns at around about 2.2 meters per second. So with a 1 kilohertz sampling rate, I can still be out by 2 or 3 millimeters finding that post edge. But D5's got fairly extreme speeds, and if without a fan, you're unlikely to corner much better than 1.5 meters per second, probably 1 meter per second for the worst corners. And so to get the same kind of accuracy, you can afford to sample at as low as 500 or even 300 samples per second and still get the same effective resolution that I see with D5 at speed. And then when you're ready to run at D5 speeds, well, you're ready to do a whole bunch of other stuff anyway. So the time of flight sensor, by the way, is used on a fair few robots, and it's used mostly in a single configuration pointing forward so that they can see a wall more than 2 cells away. They don't really care how fast. They just want to be trundling through, exploring quicker. Whether that's a real benefit or a gimmick, I have no idea. Any more? Any more questions for Duncan? Ending without preempting what he's going to say in part 2. Can you give us a kind of rough breakdown of the kind of thing that you want to cover in part 2 so we know what to look forward to?
It's more sort of system level stuff, various tweaks to give you more range. Hang on, I'd have to look at my notes, but yeah, I think it's quite interesting. Multiplexing is another topic. So you can get away with some of these Picos have only got 3 ADCs available, right? So you want to be able to get 6 sensors out of 3 ADCs at least. Things like that. It's more sort of system level stuff than the bare electronics.
Yeah, that sort of thing is really. I mean, you've got HAL, which has three sensors but 5 LEDs, so it's doing exactly that, multiplexing it.
Yeah.
This has 5 ADCs but 6 sensors, so 2 of them are directly multiplexed. So and that can be because a lot of these sensors. These side sensors, you're not interested in how far it can see. You're just interested in is there a wall there or not. And if that's the case, you don't need to be quite so well set up on certain sensors. Of course, most of the really fast mice only use about 3 sensors anyway, or 4 usually. It still gets me quite how they do so well on a few sensors. So I mean, most of our mice have got more than 4 sensors.
I have a picture on the wall of me getting younger and younger. That's how I do it. Only yesterday I came across a sensor scheme which I don't think I've seen before. It's getting hard to know what I've seen before. And what this person does is you can buy constant current. Well, they're not generators, they're constant current sinks, okay? And they can be turned on and turned off. And these, a bit like IMUs and all the other things, these have come about because of various requirements for mobile phones and so on. So they're quite tiny. And they have what I might call more sensible sized current setting resistors, right? So for doing Duncan's constant current generator, you've got to worry a little bit about getting a sub 1 ohm resistor. It's not a great deal, but it's not something you're going to have in stock. So anyway, the thing that I saw was it was a constant current sink. And what made it interesting was that it's for a half-size mouse, and he didn't have a whole bunch of room, so he only put one on, and then had that fed to a 4-to-1 analog multiplexer. So he got 3 lines coming out of the processor, an enable for the constant current sink, and 2 address lines for this 4-to-1 multiplexer, and then he would switch this constant current sink between the emitters. So 3 devices on board, 1 resistor, 2 little ICs, and 3 data lines, and he's away. His choice of multiplexer was a bit questionable because it had the data sheet says a maximum peak current of 100 milliamps, and he wants to put more through it than that. Not one, he wasn't putting 1 amp through, but there are devices with maybe 500 milliamps current capacity, which for a half-size mouse is probably plenty anyway. So that's another way to do it.
If you're looking at a half-size mouse, because it's an inverse square law, you're only going to need about a quarter of the current anyway.
Yeah, it's interesting that you were using 1 amp. I've never used anything like that. I think this one's using about 200 milliamps. I easily get 2 squares.
Using infrared?
Infrared, yeah. Or is that because, right, okay, so it's the lower efficiency of the picking it up that means you have to pump it with...
It's the relative insensitivity of the photodiode, really, because the phototransistor is going to have a gain of 50 or 100 or whatever over the photodiode. So unless you want to put an actual transient impedance amplifier in there, you've got to pump some light at it.
Yeah, as soon as you start an amplifier in, you've got to worry about the speed of the amplifier and stuff like that as well. But the other thing, of course, infrared LEDs are more efficient than visible light LEDs. So you're getting more light and you're more sensitive to it.
Right.
You can't see where it's going.
That was one thing I just wanted to add in. They do super bright red LEDs and things that are actually phosphor cooled. So they have ones that have phosphor in. So you've got to be a little bit careful of those if you're picking them.
So, anybody going to be going out and changing and redesigning their sensor boards? Or are you going to wait for part 2?
Wait for part 2 at the moment. But say every new one we do, we put something different on it. So,
I think it would be worth looking for some suitable devices. For me, that means through-hole stuff for the sensors for all sorts of reasons. But there are plenty of people who build up surface mount sensor boards, small subunits, and then mount those on the PCB, right? So you're not constrained by one thing or another. Duncan's about to go and get us one by the looks of it, and they have advantages because they can be pre-aligned. There we go.
There you go. They can be aligned in a fairly straightforward mechanical way, but they can also be reused. The Warriors, that makes a bit of difference. But yeah, build some up, people, and give it a go, because it's only by experimentation and trying out new stuff that the whole thing progresses. So good stuff. Thank you. I'm not expecting people to sort of scrap what they've got at the moment that works. That would be futile. But if you're building a new mouse, if you're starting from scratch, it's worth thinking about. And certainly I would automatically do that photo sensor change. I would put more bias across it. Just it doesn't cost you anything. It's just resistor going to a different place, sort of thing.